of two-way testing. So although I have very long slide, but I think I'll be able to, we're going to skip some, be able to finish this within 1.5 hours. Okay. Now, so first thing we're going to say today is, what is software testing? Okay. So software testing is the process of finding defect, sometimes involve executing the software of interest and validating the software against its specification. So in other words, when you talk about software testing, it's really a process of finding defects. And sometimes you don't have to execute the software itself. So contrary to popular belief, for example, a review process is actually part of software testing. So you're not necessarily, you just run the code. Software testing can also involve reviews or dry runs, okay? And when we do software testing, we are trying to validate whether or not what is actually being specified is actually, there is conformance to what is actually being specified. For example, if you throw a pen and on the floor and the pen breaks down, and the specification says that the pen breaks down, so that means the test has passed because you already fulfill the specification or the other way around. So we really have to compare what's the expected value, what's the behavior of the actual itself. Then you can know whether the testing has passed or has failed. So really, testing is actually the gatekeeper of quality. In other words, if you specify this quality, then if you conform to the specification, then you can say that the software that you have is actually of some quality. Now, so let me skip this one. Okay, why do we need software testing? Okay, software failure can lead to disastrous consequences. Okay, as a Muslim like us, okay, only God we trust. The rest we don't trust and we test. For example, okay, even if you have, for example, look at this screen, for example, you're working on a very important project. Okay, suddenly you forgot to save and you lost your data. So, and then that can be, if you're about to winning a big, for example, contract, then you might lost the contract. Okay, and you might also, for example, loss of data. You can have also loss of fortune. This is the example, one of the challenges, I think one of the space shuttle in launching, where there was a divide by zero error causing this thing to explode immediately after its launching. Okay, you can also have loss of life. For example, you have an airbag system. It's controlled by software, and the specification says that the airbag system should react within, say, 10 milliseconds upon impact. But if your software react within, say, 10 seconds instead, then you have loss of life. So really, software testing is very important, and it can lead to loss of data, loss of life, loss of fortune, and many other losses that we can think of. Okay. Now, for this reason, software testers are pessimist people. That means I will not, even if you're my roommate, I'll trust you that you're a good roommate and so forth. But when it comes to testing, when you did your code, I will always be pessimist and asking you, I don't trust you, I have to test what you did. So actually, software testers are pessimist people. Now, software are everywhere now. Okay, they are part of our lives. Everything now is becoming software. For example, you don't see anybody now having cameras, because cameras are now incorporated as part of handphones. Okay, now we use software as washing machine, for example. You see in the market, there are washing machine that's fuzzy logic. There are washing machine, for example, neural network. So, and we use it everywhere. Because why? Because software is easy to change. You know, for example, you want to customize a mechanical product. It's difficult to change to change it. But you have a washing machine, you can have different brain easily by changing how the algorithm works, rather than changing the gears, for example, for if you are doing maybe doing the old-fashioned washing machine and so forth. So we opt to software always over hardware because software are easy to customize and does not wear out easily. So this is why we opt for software a lot. Now, testing of software, because software is gatekeeper of quality. So we have to test software. That is definitely the activity that we need to do. However, testing can be a painstakingly difficult activity. Why? Because software line of code increases tremendously in the last 10 years. Maybe last 10 years, you can have a floppy drive. You have disk drive. Now you have pen drives. And the size of software is kept increasing from kilobytes, megabyte, gigabyte, and terabytes, owing to the requirement or sophistication of the user, the functionality that user wants. As a result, there's a lot of changes in terms of line of codes. So making software testing a difficult activity. So this is the key thing we have to look into. Now, let's look at this example. Let's say we took one of the tab, Microsoft Excel tab, for example. Microsoft Excel tab, there are many options. For example, if you look at the slides, for view tab, you have start, task pane, formula bar, status bar, and this one can be turned off and on. This could be true or false, and then you can all true or false, and you can automatic. For example, colors, there are 56. If you look at this, just view tab, you have 20 possible configurations. If you want to test all possible configuration, because ideally you want to test all of them, and you want to see that all values that you test, again, your software, and there's nothing wrong, and it behaves what it's supposed to do. So in this case, if you look at this, 20, you have 2 to the power of 20 times 56 possibilities, or to be exact, 58 million combinations to be tested. If you take 5 minutes to execute one possible test, then it will require 559 years to complete all the tests just for view tab options. So what we can say here is that complete and exhaustive testing is impossible, owing to the limited resource or timing constraint that we had. We cannot be testing everything. So this is the fundamental issue that we need to understand when we talk about testing. Now, for example, if you look at hardware switches, for example, here you have 34 switches. If you want to test all the switches, then you have 1.710 10 to the power 10 tests. For example, you have this one on, this one off, on, off, on, off. So you have to test all on, all off, or one is on, one is off. So the question is, which switches to be selected for testing? Okay, similarly, here, which option should I test? Okay, so this is the idea that we are talking about when we talk about T-way testing. Now, this T-way testing, the problem of having too many tests is called combinatorial explosion problem. Okay, now how we can do combinatorial explosion problem? We have so many things to test. What we can do is we can do random testing. But typically, for example, you have 100 switches. Just randomly test on, off, on, off, on, off 100 times, on and off, and then on, off. What happens is that you tend to be stressing on certain configuration. So this is having an unfair distribution of tests. You can do manual testing, but manual testing is impossible because it takes 559 years, for example, if you just for the view tab to be tested. So you can do also parallel testing, but parallel testing are getting more complex as line of codes are increasing year by year. So given limited time and resources, what are the optimal set of smaller test cases to be used for testing? So this is the question that we ask when we talk about T-way testing. How are we going to minimize number of tests, yet you do it in a systematic manner, in a way that you will not be sort of sacrificing your quality. So this is the idea that we are trying to do with T-way testing. Now, if you look at this, if you are trying to pick an orange, or you cannot test the orange, but still you want to test whether the orange is good or not. What you did is you will do sampling of orange that you want to test, and by that sampling you want to say that, hey, I've tested enough. You know, with this sampling, I've tested enough. I've tested, like I test the whole lot of orange. So I'm testing sample of orange. So the idea of T-way testing is actually we're trying to sample the test case, sample the test cases in such a way that it's manageable for testers to do the actual testing. So this is the idea. Now, when you talk about sampling, when you do testing, there's a lot of sampling techniques in testing. Okay, for example, you have equivalent partitioning, boundary value, and so forth. Okay, so the idea of sampling in software testing is actually a common thing. It's nothing new, where you cannot test everything. You need to sample the test cases accordingly. Okay, now, so there's also a software risk. When you, for example, let's say you have an iPad, for example, or ebook reader, having only 3 buttons. Okay, now in maybe year 2020, you have 20 buttons. There could also possibilities of interaction between the button that causes fault. Okay, so that is sometimes unwanted interaction that you need to test that to reduce the possibilities of fault. Okay, so this is the idea also. Now, in real life, okay, you have bacteria, maybe some bacteria maybe interacting with other bacteria and the others are not interacting. Okay, and for example, if you look at this formula, for quadratic formula, you see that x1 and x2 are actually interacting with b squared minus 4ac both way, and depending on plus or minus, the value x1 and x2 differs. So interaction is actually a real life phenomenon that we see in our real life. Okay, how do we manipulate interaction in such a way that we can use it for testing? Okay, now let's look at motivating example. I've given you the view tab for Microsoft Excel, but that's too large. So let me give you, let's say we have a simple pizza ordering menu whose crust is having 2 possible value, classic and toss, and then crunchy thin. Okay, and flavor having 2 value, vegetarian and pepperoni delight. Okay, and then topping having 2 values, pineapple and beef. Deliveries has 2 values, eat in and take away. If I represent this as A1 and A2 as being this value, so I'm going to have the possibilities of A is A1 and A2, B is B1 and 2, C is C1 and 2, and D, D1 and D2. Similarly, I could have this home security system where smoke detector having high or normal, active or inactive, high or low, security panel of this. You can represent this, okay, as this set of parameters. Smoke detector can be high or normal, glass break door can be active. You can see that even though it comes from a different sort of set of problems, you can say that you still have the same number of, this is called, I'm going to introduce a new thing, this is called parameters, and this is called values. Okay, this is the parameters A, B, C, D, and the values for A are A1, A2, B1, B2, C1, C2, and D1, D2, and you can also map this into this set, similar set. Okay, now the idea here is that now when you look at this, if you represent this input variable, the parameters as A, B, C, D, and you represent the base value A1, A2, B1, C2, D2, C1, C2, and D1, D2. When you look at, I'm going to introduce a new term here, at interactions, and when they are all interacting, there are 4 variables. So when they are all interacting with interaction strength of 4, then the exhaustive combination of tests is going to be A1, B1, C1, D1, A1, you can have A1, B1, C1, D1, A1, B1, C2, D1, A1, B1, C2, D2, and so forth. If you do this exhaustively, you will get a 16 combination, because it's actually 2 times 2 times 2 times 2, which is actually the exhaustive possible combination is actually 16. So in other words, if you go back to this, you see that you need to test this. If you want to test everything, you require 16 test cases. Then you have tested everything. So the question is, what if we relax or compromise the interaction strength? So rather than working with t equal to 2 or t equal to 4, meaning I have 4 variables, t equal to 4, mean I'm interacting all variables at the same time. If I consider only 3-way interaction, that means I'm only considering the possibility of there are 4 variables, A, B, C, A, B, D, B, C, D, A, C, D. If you consider A, B, C, and then what you do is, when you consider A, B, C, the D, you put anything, don't care values. Any values, valid values, either D1, you could put all D1 or all D2 or a combination of D1 and D2. And you could also look, for example, A, B, D, and A, B, D, A, B, D, and then the C is actually a random value. And you could look into A, C, D, okay, and A, C, D, B is a random value. And then you could look only also at B, C, D. Then this is a random value. In other words, what I'm trying to do is I'm going to look at interaction of t equal to 3. Okay, now here, when you did this, when you find the 3-way interaction, when you combine all the 3 or the 4 actually, what you do at t equal to 3, because you consider only 3 at a time, you get this value. Whenever there is repetition, you delete them from the screen. So in the end, you get the reduction from 16 originally now to 13. In other words, when you look at the interaction of variable, you sort of compromise the interaction. What you do is, so there's a mistake here. This should be in the slide. Where's my mouse? Okay. But it's okay. You will see that you have a reduction from 16 to 13. This should not be there, because this is the base value, only the bottom one. Now you see that when you did this, you got the reduction from 16 to 13. That means when you compromise the interaction strength, you can reduce the test cases further from originally from 16, now you become 13. Okay, what if you reduce, and when you do demonstration of correctness, you find that when you need A1, B1, C1, 3 pair, all the 3 pair has to be covered, and you see, yes, indeed, all the 3 pairs are covered by these test cases. So in other words, there is a reduction of 18% of the test case originally of 16 becoming 13 by relaxing the interaction strength of t equal to 3 instead of using t equal to 4 at full strength. Now, if you relax the t further, okay, now instead of doing a 3-way, and we look at 2-way. When in 2-way we have AB, you can have AC, you can have AD, you can have BC, you can have BD, and you can have CD. Now, doing the same thing where when you have AB, you randomize, you can be C1 all the time, or D1 or D2 all the time, because they are random. You take these values, take all the 6 values, add up together, and remove repetition from any of the values. When t equal to 2, the test case now become 9. So you have reduced the test case from 16 to 9 at t equal to 2. Of course, you cannot do t equal to 1 because there's no interaction. Because fundamentally, we're talking about interaction. If t equal to 1, there's no interaction. So in other words, you can go from t from the maximum number of parameters to t equal to 2. Okay, in the end, when t equal to 2, you get further reduction of test cases from 16 to 9. Now, yes, when you do this, when you do t equal to 2, or sometimes called pairwise testing, you can have better set of tests. For example, 10 to the power 20, when you pairwise, is about 180 test cases. When you have 3 to the power 13, 1.5 million test cases, you get only 15 test cases. Okay, 281, you get 9 test cases. So yes, pairwise testing saves time and cost. But in real life, there are some require pairwise. Some system they require pairwise testing, but some system may require more than pairwise testing. So we can do, for example, cumulative t equal to 2, t equal to 3. So you get whatever values that you get from t equal to 3 and whatever t equal to 2 that you did just now with 9 and 13. When you combine the two, you get a reduction from 16 to 14. So in other words, you can have cumulative, meaning you can consider t equal to 3 and t equal to 2, and you combine the result, you get, there is still a reduction from 16 to 40. So now you can also look into something called mixed strengths or variable strength that you can have, for example, at t equal to 2 for certain particular variable, and then certain for the other particular variable, you get t equal to 3, and this is called variable strength. So when you have variable strength here, when you did this, you combine the result from this t equal to 2 to t equal to 3, and you get reduction to 13. You still get reduction. So there's possibility for you to do various number of t's. You can do cumulative, you can do variable strength, a combination of more than one strength for you to be able to generate the set of test cases. So there is a reduction from 16 to 13 when you did this. Okay. So the point I want to make is that T-way testing can help you systematically reduce the number of exhaustive tests you want to do your testing. You can minimize, but based on interaction of variables. So this is the point we want to say now. So something to ponder about, which is the good choice for applying variable strength, for example. Okay. If you compare, for example, this one and this one, when you look at this t equal to 2, meaning you relax a lot of variables, but here you make it strict for certain variable. Okay, but here you already make it strict for this variable and you relax, well, you relax a little bit. So which one is actually, this one or this one is better? The answer is this one is better, because this one you relax all the 4 variables, but you put very more stronger strength to 3 variables. Here you make all strong. It doesn't make sense to have all stronger. Suddenly you make rather a relaxed one for this one. So that's why this is a good one. This is not a good one. And this is also a good one. We can have two having the same strength as cumulative. Okay, but this is not a good choice of applying so-called variable strength. Now, something to ponder, if you look at the Venn diagram, if you have a set of test cases represented by t equal to 2, and a set of test cases represented by t equal to 3, which one is actually the right one? Can T3 cover T2, or can T2 cover T3, or they are having some overlapping values of test cases? So is ST2 a subset of T3, or ST3 a subset of the set of T2, the test case for T2? Now, the answer is this. Okay, sometimes it's not the whole subset, but ST2 and ST3, they are overlapping. But there are cases, there are some, but there's two possibilities. They could be this, they could be also this, but they cannot be this because they have to be T equal 2 and T equal 3. They're bound to be overlaps, but there are special case that the overlap is like this. Okay, or like this, but it cannot be like this. It cannot be. So this is wrong. This is wrong. This could be right, and this also could be right, depending on the number of parameters and number of values that you have. Because originally, all this thing comes from the idea from covering array. Some covering array are very so-called mathematically, they have some property that they share with each other, but some are not. So that result this into this or that. Okay. Now, so what we have learned, we have achieved test reduction, and then we cater for fault due to interaction. When we did T-way testing, if, for example, you did T equal to 2, whenever you run the test and you found no error, we can conclude that, hey, that this software has no interaction, pairwise interaction between all the variables, all parameters. You can make that conclusion. Okay, so the solution, the range of interaction coverage is 2 less than T less than maximum number of defined parameters. If you have 4 defined parameters, then the full strength is T equal to 4. The minimum is T equal to 2. We cannot have T equal to 1 because this is interaction. And the solution space is not complete as long as the interaction is covered. So there's always an optimum test size. In other words, when you use the different methods, typically you arrive at a different result. Because remember that when you did the test generation, we use randomized values. When you do, it depends how you randomize the value. If you sometimes you randomize, you get different values. So that means the number of test cases are not unique. They're often the best optimum size, depending on your algorithm. Okay. So we learned today is that there are 4 possibilities of applying T-way testing. You can do uniform strength, or meaning T-way strength, just one strength. You can have cumulative strength, or you can have variable strength. Okay, which is the most effective strategy for testing? It depends on circumstances, because it depends on the problem. You have to know the problem before, how it's solved, and what are the typical error that usually occur in this type of systems, and then you can decide. So if you look at the analogy of a chef knife, where, you know, some of the knife, for example, this is cake knife, okay, then you cannot use this to cut chicken because they're cake knife. You can cut, but it's not as effective. And then you have different type of knife. You can, all are knife. You can use it, but the effectiveness of this knife depending on the problem at hand. So similarly, for T-way testing, the sort of effectiveness of interaction, you have to know what kind of problem you're dealing with. You have to make experiment to see, oh, there are many interactions on this, so I should use, you know, maybe a variable strength, or I could use this cumulative strength whatsoever. So it is up to the tester himself to know what kind of problem he's solving, then he can solve it better. So similarly, if you use a chef knife, if you're trying to cut, let's say, lembu korban, okay? How can you use lembu korban to use this kind of, you know, maybe cake knife? You cannot cut the beef or the cow beef with this kind of knife. You can, but it's difficult. So similarly, this is the idea of T-way testing. So now in the context of software testing, where this T-way testing is applicable, how do you you know, apply this? So when you look at testing activities, before you do testing, you need to plan. Okay, then you need to plan. You need to develop the test, and then you need to check what are the, you know, whether the oracle, whether the test has passed or failed. You have to check whether you run this test what is the expected value, what is the actual value. Okay, so when you develop a test, then you need to execute the test. So the part of the develop the test, you can use T-way testing as a way to develop tests. Okay, you can execute, and then you can look whether you can stop testing or you can redesign the test and so forth. Depending, maybe if you're doing testing, maybe some people are looking at this, maybe requirement coverage. I've covered all requirements, I did test, and I can stop testing. Or maybe some people look at the code coverage. Okay, so different people have different coverage criteria before to stop testing. So ideally, T-way testing can be used when you do test planning to generate the test. Contrary to popular belief, later we'll show you how this T-way testing sort of complements other testing techniques, for example, equivalent partitioning, boundary value, how T-way testing can complement them in order for you to do testing. Now, when you do, like I said earlier, you need to be able to sort of have a feeling on the software that you're using, what kind of interaction that software has. So normally you look at failure empirical data or this similar kind of system, always having this interaction between this. From that you decide, and then you can decide your test generation. And this test generator is actually your T-way test generator. You can execute, and you can look at the test outcome, whether there's conformance to the test, whether you pass or fail. So this is the idea how it fits. And also you can look this into high level of product life cycle. You can do validation testing when software implementation, for example. This one, independent team could look from specification, from implementation, and then you can develop test case also. This one can happen using validation phase. Okay, and at the same time, what level, at any level you can do. For example, you can do a system testing, acceptance testing, integration testing, even unit testing. So T-way testing is applicable in this level depending on the problem at hand. Later, toward the end of the lecture, I'll show you some example how we apply this T-way testing to do testing. Now, now T-way testing is actually an optimization problem. Because remember that when I showed you just now, when you do interaction between, let's say, 4 variables, two-way, A, B, and you have CD. CD is you generate with the random number. So with that random number, if you choose a poor random number, then you have a larger size of test suite. So in other words, what you did is this is actually an optimization problem where you want to maximize interaction. For example, okay, and we have this 3 parameters, 2 values. Exhaustively, you have 8 possible values. But when you talk about interaction of two-way, that means you have AB, AC, and BC. And T tuples that you need to cover is AB is A1, B1, A1, B2, A2, B1, A2, B2. In other words, I have to cover A1, B1, A2, B2, A1, B2, A2, B1, A2, B2. And I need to cover A1, C1, A1, C2, I need to cover this one, and I need to cover B. So I don't care whatever here, but I want to select this value such that I will maximize the coverage, T-way tuple coverage. So that's what I'm going to do now. For example, if I take A1, B1, C1, that means I cover A1, B1, I cover also A1, C1, and I cover B1, C1. So in this thing, I've covered 3 tuples. Okay, now the percentage of coverage is 25%. Now, if I take A1, B2, and C2, then I cover A1, B2, A1, C2, B2, and C2, which is 2, 6, and 12. I could have, for example, choose A1, B2, C1. But when I do that, if A1, B2, A1, C1 has already been covered previously. So if I put this one as A1, C1, there's no, I did not maximize the weight that I have. That's why if I could choose this, but if the choice of C1 for this one is not good because A1, C1 has already been covered before. Meaning when I covered A1, C1 previously, Now, if I choose A1, B2, C1, then I have A1, B2. This is new, which is not yet covered. A1, B2 is not yet covered. Okay. There, A1, B2 not yet covered. The blue one, not yet covered. And then I have A1, C. If I choose B2, C1, if this is C1, then B2, C1 has not yet been covered. I can have B2, C1 has not yet been covered. But if I choose this one, A1, C1, because it's C1, A1 has already been covered. That means my coverage, if I use A1, B2, C1, is actually only 2. But if I choose A1, B2, C2, I have a coverage of 3. So meaning that I have more coverage with this one. That's why this is the most efficient value for C for this case, which is C2, not C1. If C1, I've covered only 2, not instead of 3. So when you did this, this is when you do efficiently doing this, you actually have the most minimum test size is actually 4 with 50% reduction. Okay, so by sort of judicially selecting the right values can have more reduction on the test cases, but yet still having the same coverage of tuples that you need to cover, coverage of interaction that required to be covered. Okay, now, so this test suit generation can be formulated as optimization problem. This is actually an optimization problem, or sometimes called search-based software engineering problem. Okay, now search-based software engineering problem, actually you apply search technique guided by fitness function to capture the properties that are acceptable artifact. You see, basically what you want to maximize the number of coverage in the test case that you select. Okay, so this is sometimes more specifically, you can say that this is also called a subset of search-based software engineering, or called search-based software testing problem. Okay, now when the parameter is large, the parameter meaning, like just now when we talk about parameters, parameter meaning A, B, C, D, E, F, G, is impossible to run test suite manually. So many existing deal with this T-way test generation problem using meta-heuristic or hyper-heuristic algorithm. They're also public domain tools. You can look at this. Is also, I have my own tool. Okay, also T-way testing, free for research use. Okay, you can find other tools also where you can see how you can use it to generate T-way test suite. Because if you have 4 parameters or 5 parameters, you have so many possibilities. It's possible to do by hand. You need a tool to do T-way testing. With hand, generating tests would take a lot of time if you want to do manually by hand. Okay, now we've been working a lot on T-way testing using meta-heuristic or optimization algorithm, and also we use hyper-heuristic. Our work on T-way, we've been doing this for the past 10 or 15 years doing this. Okay, so we work with something called hyper-heuristic, where is actually a meta of meta-heuristic, where another level of meta-heuristic is controlling a set of low-level meta-heuristic. So this is called hyper-heuristic, where this hyper-heuristic works as penalizing and rewarding. For example, the analogy is this simple Avengers behavior. For example, you can imagine this being, for example, particle swarm algorithm, and you have this. So what this guy will do will say, this sort of master will say, particle swarm, do your optimization, and the particle swarm is doing well. So when the particle swarm is doing well, he is being rewarded, and then we're able to run it again in the next iteration. Now, if, for example, particle swarm is having a problem, then this will be penalized. He will be penalized, and the controller will give another chance to other meta-heuristic, for example. So this is the idea of hyper-heuristic. So people can solve this problem of T-way testing as optimization problem using meta-heuristic approach or hyper-heuristic approach. And this is being an adaptive behavior where you can penalize and reward the best performing meta-heuristic algorithm for them to perform the search for you. And we did a lot of work on this. This is past 3 years. We have many hyper-heuristic approach solution to it, and we also have this hyperheuristic. We also have hyperheuristic. We also have meta-heuristic approach to solve this T-way test generation. So we have this is last 3 years. We have many from the past 10 years also. So I've given you the feeling of what is the basic of T-way testing is based on interaction, and then it's actually an optimization problem where you can use optimization algorithm to solve it, and because this is NP complete problems, you can have different ways solution you solve, you get different answers, maybe different performance, different size, better size than the previous methods. So you can always have this algorithm to solve this if you're doing research on this. Now I'm going to share with you some mathematical notation, because if you understand the mathematical notation, then you can understand the papers when you read. When you read the papers on T-way testing, if you understand the mathematical notation, then you understand what the paper is talking about. Okay, so if you remember that there are 3 possibilities applying on T-way testing. This is called uniform strength, only one strength, cumulative strength, or variable strength, where in this case variable strength T2 must be larger than T1. Okay, you cannot be a T1 larger than T2. So this is, you can have this if you remember what we did before. Now here, okay, we can represent using something called the covering array notation, where n is the number size, t is the t, v is the value, and p is the parameters. Okay, and so when you use this, this is called covering array. This is the mathematical notation, and you can also have mixed covering array as the notation. Now, if you look at this, for example, from you can have. Let me give an example first, and then we come back to this. Okay, remember that we did this previously in the previous slide, where you reduce the test case from 16 to 13 when you take t equal to 3. Now, the way to express this is CA, n is the total test size, 3 is a t, and this is the value, which are 2 values, and you have 4 parameters. So this actually, we have 4 parameters, you have 2 values, and you represent this notation for this result as CA 13, 3, 2 to the power of 4. That tells you this is number of test cases, this is t, this is the values, this is the parameter, 4 parameters. Okay. Now, similarly, we did this for cumulative. Okay, for cumulative here, or we did a variable strength here first. Okay, let me do cumulative first. Okay, now for the cumulative first, you have 14 is the final test case, 2 is t equal to 2, and then 2 to the power of 4, meaning the values, the parameter 4, there are 2 values. Okay, and this is cumulative. Okay, and this is there should be a, if you look at this, remember that when you have a cumulative, we have this. I didn't put it. You should have this at t equal to 2, covering all 4 variables. This t, you have to have this t equal to 2, and then t equal to 3 also to the all 4 variables. This is why you have CA 3, 2 to the power of 4, meaning you have at value 4 t equal to 2, because this is cumulative. Cumulative meaning all is covering the same parameters. Okay. Now, similarly, if you do variable strength, you have 13 is the result, t equal to 2 is for the whole 4 parameters. Okay, 2 to the power 4, and the CA with t equal to 3 just for the 3 variables. Okay, 2 to the power 3 just for the 3 variables. So this is why how you can express this into mathematical notation. So if I go back here for variable strength like this, you call it VCA, meaning that you have this one 12, the final test suit size t equal to 2 for 3 value, 2 parameter, 2 value, 2 parameter, and then you have t equal to 3 for 1 parameter, 3 value, and 2 parameters, 2 values. Okay, you can express this in terms of this notation. Okay. Now, so application of this notation, we've looked into it. Now, you can make sense. For example, if you read this, if you read many of the T-way testing papers, you'll find something like this. For example, CAN 2, 3 to the power 4. That means n is actually this value 9, t equal to 2, and they have 3 values but 4 parameters. That means you have 4 parameters A, B, C, D, and each parameter having 3 values. So if you're able to read this, then you have a mixed covering array. Mixed covering array is when you have the values are not the same. Okay, for this one, you have 1 parameter of 5 values, 8 parameters of 3 values, 2 parameters of 2 values, the 8 parameters of 3 values. Okay, so when you do this, this is t equal to 2. With this one, you get, for example, this algorithm will give 19, this algorithm will be 20, this algorithm will give 15, and so forth. This is the number of test cases generated from this set of test cases. Okay. Now, similarly, here you have 1 parameter having 6 values, 1 parameter having 5 values, 6 parameters having 4 values, 8 parameters having 3 values, and 3 parameters having 2 values. And you have this total set. You can see that the number of test size differs a lot. Okay, some get 45, depending on the algorithm that you use. Okay, you have this. This is mixed covering array. Mixed meaning the number of values are not the same. You can have also variable strength, where you have more than one strength. For example, here you have 15 parameters, each with 3 values. Okay, and then you have a sub CA here of 3 parameters of 3 values with having t equal to 3, meaning out of 15 parameters, 3 of its value, we also put t equal to 2 as the interaction strength. So you have this called variable strength. So very importantly, if you want to understand T-way testing problem, you need to understand how to read the tables. Then what is the result means? Because this 3 to the power t could be coming from different set of problems, but having the same parameters. Like the example we gave before, we gave example of a pizza screen and a alarm system. Although they come from different problem, but they can actually be of a same covering array representation, mathematical representation. So this is actually way you can make sense of the tables. Now, you can also having a different combination. If you understand this table, then you can work in this area. You know, it's not difficult to understand the table. This one, because is actually v to the power of p. This is 15 parameter, each of which having 3 values. You know, and then this CA part of it, meaning this is 4 of its value having interaction of t equal to 4. In other words, you have to, whenever you have the main configuration, t has to be smaller than the inner configuration of t. Okay, so when you do this, there are different tools that we had, and there are different results that you can get. Okay, now let me share with you some application of T-way testing. Now, you can use T-way testing, for example, to predicate testing. For example, you have a set of Boolean expression x greater than 10 and y less than minus 10 and not open equal to true. And when you represent this as A, B, and C, then you have A and B and C. A is actually x greater than 10, B is actually y less or equal to minus 10, and C is equal to open is true or false. Okay, now when you do this, if you want to test everything for this, this is the base value. A having false or true, B having false or true, C having false or true. Meaning A, this possibility of this test is false and true. The possibility of this also false and true, and this also false and true. If you look at this, you have total all in all 8 possible test cases if you want to test this sort of expression exhaustively. Okay, you have 8 possibilities if you want to test everything exhaustively. Now, now if you use this technique that we had, okay, you look at, for example, just pairwise, meaning t equal to 2. So meaning if t equal to 2, I'm going to cover A, B. So I'm going to FF, FT, TF, TT, and I'm going to select this C randomly or maybe in an efficient way. Okay, and I'm going to look at AC. Okay, you have AC, which is FF, FT, TF, and so forth. And I'm going to look at BC, FF, FT, TF, and TT, and all this. You have this the A value of you want to optimize them. Okay. Now, when you do this, the exhaustively, you learn this from your 0, 0, 1, 1, 4 times, 1, 4 times. You learn this from your binary or from your logic design, whatever, logic programming, whatever. You learn you get 8. But for optimal this, you can actually for pairwise coverage, this is the most minimum. FF, you cover all the pairwise one. FF, FT, TF, FT. You cover all this, meaning we've covered. If I use this FFF, I put FFF, I cover AB, I cover AC, I cover BC. If you follow this, this is the most optimal test suite that I want to do for this one. Now, you get, this is the test, what you need to do. Then you have to convert this, A comes from this, X greater than 10. Then this has to be false. So you need to find A less than 10, which is 9, because this is a false value. Okay, and B, you get false value. Y less than -10 is actually a true value. So I put the false value, B equal to -1. I put this -1, meaning Y equal to -. I'm sorry, this should be not A. This is actually X. This is actually Y. Okay, so not A and B. A and B is the variable. It's not the variable. This is the condition or predicate. We want to have X equal to 9, and then this is Y equal to -1, because this is less than -10. Okay, so this is true. So you have to select the set of test cases that satisfies this. For example, test 3 now, you have this is true. True mean A greater than 10, so I put 11, greater than 10, and I B false, less than 0, so I put equal to 0, less than -10, I put equal to 0, and this is true, so I make it equal to true, and so forth. So this is actual test cases. Again, excuse me that this actually should have been X, this should have been Y. Okay, and this is actually the optimal test suite that you want. If you want to use this to test the expression given like this. Okay, now let's say different application. Okay, this one when you apply to predicate testing, let's look at how you apply this to unit testing. Okay, let's say you have a function. Okay, a C function, say valve control. Okay, having 3 inputs: pressure, temperature, and Boolean. Okay, and then you need to find what is the values that is good to test this function that you want to test, or unit testing that you want to test. Okay, let's say this is a unit. Now, what you can do is, from your testing, I hope you learn from your testing, what you can do, you can use something called equivalent partitioning and boundary values. For example, you know that pressure is between less or equal to 10. Okay, and pressure can also have greater or equal to 100, and temperature greater or equal to 27, and set can be true or false. So you can use equivalent partitioning and boundary value to generate a set of test cases for you to be able to test valve control. Now, remember that when you do equivalent partitioning, primarily you divide the test into partitions and each partition is equivalent. You know, when you have any set, but they are equivalent based on the partition. This is called equivalent partitioning. So in other words, you have a partitioning of valid or invalid. For example, between 1 to 100 is valid. We can put this 99, 50, 49, 2, 3, 4. It doesn't matter, but they are all the same partition. So we assume that when you have the same partition, you have test that partition, and you have an invalid partition, and another invalid partition. So this is called equivalent partitioning. So contrary to popular belief, if you put, let's say, one test case of equal to 2 and one test of equal to 3 or equal to 50, you are wasting test cases because they are all from the same partition. Okay, I mean, the same partition, ideally, then they behave the same because they are the same partition. Even though the numbers are different, your test case may be longer, but they're coming from the same partition. Ideally, that's not a good value, because you want, when you do equivalent partitioning, you want to sample the test case based on different partitions, not from the same partition. Otherwise, they are the same result, the same value, although or not the same, but the same result because they are the same partition. So this is actually equivalent partitioning. You also learn about boundary value. This is just when you do testing, you learn boundary value, I suppose, where you should look near the boundaries, at the boundaries, and just after the boundaries. Okay, and then you find the boundaries. So for this type of cases, you're given this less or equal to 10. You can check equivalent partitioning and boundary value for you to get a good set of tests to be able to test for this. So rule of thumb here, you always do at the boundary, you know, just before the boundary, at the boundary, and at the other boundary, and just above the other boundary. You don't need to put inside, because inside the equivalent partitioning. If you have this one, you can have just before, at the boundary, and then at the boundary, okay, and then this one, and at the other boundary, just before this. This is a rule of thumb you can use. Always before, at the boundary, and then at the boundary of the other side, and after it, and what's inside is equivalent partitioning. So this is how equivalent partitioning and boundary value differs. Okay. Now, if you did this problem, remember pressure. This is pressure less or equal to 10, and this is also greater or equal to 100. And when you're less or equal to 10, you open the valve. Okay, and then you, in between, you shut down because there's an else there, and then after 100 you do valve close. Okay, and similarly for temperature, 27 you enable cooling coil greater than 27 equal to 27. This one you would disable cooling coil, and you have a set. You don't have boundary value set because set to value true or false. So if you look at this, if I were to find the equivalent partitioning for pressure set of test possibility I have, because this one partition here and the other partition in the middle and the other partition here. So you have 5, and I can have 30, I can have 120, I could have, you know, 2, 3, 1, whatever. This I could have, you know, 50 or 60, whatever. But in this 120, I can have 130, 140, it doesn't matter. But because they are all equivalent, so I have a pressure equivalent partitioning having this set of possible tests that I need to test it with. For boundary value, I need to test at 9 at the boundary, and then at 100, and then at 101. Because this is an integer, an increment of integer is 1. That's why I have this one. So in other words, I don't need to put anything here because here is actually equivalent partitioning already. So if I look at this, for equivalent partitioning, I have this boundary value, I have this boundary value. Similarly, I did for temperature, equivalent partitioning is 20, because this is partition here, I can have 50. And for boundary value, I can have 26, 27, and 28. And this one should be true and false. So these are my set of test cases that I'm going to use to be able to test this unit or these methods, you call it. Okay. Now, by having this raw test case, I'm going to have 5, 10, 20. These are the base value. This is the 3 parameters. One parameter having 7 values. The other parameter having 5 values. The other parameter having 2 values. Okay. Now, if I want to represent this as in covering array notation, I'm going to have CA n, comma 2. Then I'm going to have 2, 4, 6, 7. Okay, 7 to the power of 1, and then 5 to the power of 1, and then 2 to the power of 1. Okay, yeah, is values power parameter. Yeah, I can represent this in covering array if I want to. Okay, now if I look at this, if I want to do exhaustive combination for this, I'm going to have 7 times 5 times 2, which I have 70 test cases. So in other words, even though I'm using equivalent partitioning boundary technique in testing, you have a lot of test cases to do with. Okay. Now, if you use interaction testing t equal to 2, you can reduce the test case only 35. Of course, you cannot do by hand this one. You really have to use a tool to do it. But I can show it to you. This is the set of test cases that you can do. For example, test 1, 4 to 1, meaning 4 is actually item number 4, which is 0, 1, 2, 3, 4 is 10. So the value I need to use is 10, and the value is 26, and set has to be false. And this is the test case that I have, and this is the actual translated this into the actual values that I have, and I have my expected results. They say assume that there's no funny thing happens, there's no funny thing, no anomalies. So I have all the 35 cases that I have here, instead of having 70 set of test cases. Okay, you can reduce it. Of course, you cannot do this by hand. You need to use a tool. Using my hand is difficult. There are many tools around. Okay, you can use this to solve this problem. Now, you can do T-way testing for configuration testing. This is from one of the papers that we did. We have this different options that we have. We want to find the best options. We can use T-way test. This one we use T equal to 3. That maps into 1 parameter to 1 parameter of 3 values. Okay, and you have 4 parameters of two values. Okay, and there should not be a comma here. Okay, there's a comma. There's a mistake. There should not be a comma, but you can see this how this one is represented in covering array. And this is the actual for t equal to 2. If you look at this, 3 times 2 times 2 times 2 times 2. This is for 16 times 3. This, if you do exhaustively, 16 times 3. But here with this, you can only have 17 only. So you can reduce the set of tests by doing interaction testing. Okay. Now, how effective is T-way testing? We did many experiments in our papers. We did, for example, this one was from the old paper we had. If you want to test this file chooser demo, we have 73,000 set of test cases, 1 4 value, 2 3 value, 11 2 value. If you represent this CA and 2, we have 4 to the power 1, 3 to the power of 2, and 2 to the power 11. Okay, yeah, if you want to represent in covering array, you can represent like that. Okay, and then here, when we did this, we have this set of parameters, and this is the 15 test cases that instead of having 70,000, we have only 15 test cases, and these are the test cases for us to test all the parameters that we had, parameter, metal, motif, window classic, whatever. So this is the set of parameters we can do the testing. Okay, and when we did the coverage, even though we did t equal to 2, we get a method coverage 83%, block coverage 96%, line coverage 94%. That means we get a very good coverage, even though we only did with 15 test cases instead of 73,728 test cases. So we can get a good set of coverage of the testing. Okay. We did this in one of our papers also. We test Flex. Flex is actually an application open from software infrastructure repository, where this is actually the parameters of Flex, and we tested with 2-way, 3-way, 4-way, 5-way, 6-way, and exhaustively you got 4,608. And then these are the one, as you know, when you relax more, you get less test cases. So when you have this, so we use this to test Flex in our papers, and we found that with 4-way testing is equivalent to exhaustive testing with function coverage of 83%. That means I don't have to go to exhaustive. I can only use 4-way, and with 4-way, with 4-way, I already have 764, but I get the same coverage of 4,608 set of tests. Okay, so this is what this. Okay, so I'm done with this. So thank you for listening. If you want to ask question, feel free to ask any question. Thank you. So I think we have another half an hour to 40 minutes for question and answer.
Yeah. Thank you, Professor. Well, we have some questions in the group chat, I suppose.
Okay.
Yeah.
Well,
there are 5 or 6 questions, I suppose.
Wait, let me, how do I stop share?
Yeah.
Okay. Oh, there are many
First
questions.
question in Indonesia. Is it okay?
It's fine. I understand. I understand.
Okay.
I speak. We
From
speak.
Muhammad Rizki.
Okay.
The first from Muhammad Rizki. Is there any risk analysis process in testing activity?
Okay. Yeah. Whenever you do testing, you really have to identify the risk. Okay. And, for example, you have so many things to test. One of the ways you want to prioritize your tests. Let's say you cannot test everything. You have so many things to test. So you have to do risk analysis. For example, if I look at if this set of failure happens, this very high risk. For example, the other set of problem, very low risk. Then I would test a lot from the one that having higher risk, because testing often happens towards the end of the development, and you don't have time to, for example, if you're doing design, you can always extend because you have a lot more time. But with testing, you are toward the end. People want to release the software. So what you need to do, you really have to prioritize which test to run. And that requires a lot of risk analysis. That means it's very risky, then you need to test them more. No risk, then you don't test much. So that's why you need to have risk analysis to prioritize the test that you want to do. So that's the answer for that.
Okay, thank you.
There's a question, how do you prioritize test case and combinatorial testing?
Yeah, so I think it relates.
Okay, you can prioritize. You can. We have 3 papers that we did where we prioritize. We prioritize test case by the tuple coverage. Okay, there are papers that we wrote, few papers that we wrote where we do prioritize T-way testing, meaning you prioritize the one that test cases having the most coverage first. Because when you do T-way testing, you want to cover the interaction. The one having higher interaction, you cover the most. You can prioritize that. If you want to prioritize based on that. Okay, you can do prioritize this. Okay.
All right, thank you. And then we go to the next questions. In the perspective of V-model in software development, when the T-way testing is conducted, in unit, integration, or system testing?
Okay.
From Ivan.
Okay, it depends. Okay, when you do, you have to understand. Okay, like if you are a chef, you're a chef. Meaning you're tukang masak. In Malaysia we call it tukang masak. I don't know in Indonesia you call it what? Okay.
Koki.
Tukang masak ini yang masak. Okay.
Yeah.
Okay, chef. Okay. And then you are given, okay, bake a cake. Okay. So when you bake a cake, then you want to use which knife? Then you probably will use the knife for the cake. You won't use the, kapak. You know what kapak means? Axe.
Yeah.
Kapak, I don't know whether in Indonesia call it kapak also, where you cut trees with kapak. You don't use kapak to cut the cake. So it's actually, it's up to the tester himself to know what kind of problem he's having, and from there he can choose the right. For V&V, it depends on what kind of V&V you're using, what kind of system you are testing. Then you have to be able. Sometimes T-way testing is not applicable. You don't need T-way testing. There's no interaction at all. Historically, this problem having no interaction. You don't use T-way testing. You use just equivalent partitioning, boundary values, or other techniques, decision tables, because T-way testing does not replace other technique. It's just an alternative to other technique. Because pisau itu bukan untuk one pisau solve all, cut all. This pisau for particular thing that you task at hand. If you this kind of problem, no interaction, is wasteful to use T-way testing because it's not useful. So it depends on the problem. So I hope that answers the question.
Yeah, thank you. And then from Muhammad Rizki, what should we learn to be able to do software testing?
Oh, okay.
Prior knowledge or something.
well, software testing. First, I've always said I'm not trying to be what I call gender bias or whatever. But software testing is in Malay they call it somebody. In English they call it pessimistic. But in Malay they call it like women. They like cerewet. You know what cerewet means?
Yeah.
Your wife, apa bang ini kenapa itu. So tester is only suitable for women. I'm not trying to be gender bias, but women are a bit male are a little bit. It's okay, it's fine. Kurang lebih okay male, but the women they always no like that, no like this. So to be a tester, you really have to be this character of cerewet. Always want to know why you. I don't trust you. Even if you're my roommate, I don't trust you. If you're my husband, I don't trust you. You go out at night, are you going out to meet your friend or you meet your girlfriend, whatever. So you really have to be pessimistic. Then if you have that passion to be pessimistic, then you'll be a good tester, because tester, need to be someone who are very, in Malay call it cerewet. I don't know what cerewet is. That a word in Indonesia?
It's the same word.
Cerewet means always si itu salah, ini salah, apa pun salah. Okay, this is tester. If you want to be tester, you have to be behave like that. Pessimist people. Okay, hope that answers the question.
Yeah, thank you. And then the next question from Fata Muria. Is it safe to use T-way strategy to find defect or critical software like self-driving car, considering it doesn't cover all of the possibilities?
It's a good question.
Yeah,
it's
how
really
to
a good question. But
the chance.
But you have to understand this, okay? T-way testing does not replace other testing methods. You cannot just test for safety software, just use T-way testing. Cannot. What T-way testing does is that it tells you that you did T-way testing, the software that you have does not have interaction faults. That's the only thing you can conclude. If I did T-way equal to 2, no fault found, I can say that, okay, for this particular application, there is no interaction between two parameters of the software involved. You can make that conclusion only. You cannot say, oh, now T-way testing passed. Conclusion, okay, you're safe. You can use it safely. No, it doesn't. T-way testing complements other techniques that it finds interaction test. There are interactions between parameters. You can be sure if there's no test, there's no faults, or there's no failure in the test, you can say that, hey, this application is free from fault between two parameters if t equal to 2. You can only say that. So that's the answer. Should be the answer.
Okay. And there's an additional questions: how to minimize the chance that some critical defect when unnoticed without adding too much computational load?
Oh, this is okay.
Yeah.
uh, this is it depends. Okay, when this relates to the idea of when to stop testing. Okay,
Yeah.
when you do testing, okay, when are you going to stop testing? Are you going to stop testing? Let's say if you have the test period of 2 weeks, are you going to stop testing when the period ends in 2 weeks? Or are you going to stop testing when there is a good code coverage, functional coverage? For example, you said code coverage of over 80%, I'm going to stop testing. Or is that you're going to stop testing when the functionality, you test, you test the functionality and all the functionality, you test all the functionality and you have no faults, then you say you stop testing. So this relates to the idea of if you want to stop testing, typically you stop testing when you based on functionality. For example, you have user defined, let's say, 100 functionalities. So we test against all the functionalities. And then if there's no error, then normally we typically stop testing. But some people, they do a bit more. Not on that, we also go further by looking at the coverage. Meaning when you talk, say not only functionality, but also the code coverage. For example, functional coverage, you want 90%. So you will start testing again, not until you reach 90% of coverage, then you stop. So it depends. If you want to do more testing, then you measure more. You want to do code coverage, then you have to do a lot more testing. But you want to do functional coverage, then slightly less. Because functional meaning if I did A, B, I should get C. And you check A, B, I get C. And then B, D, I get E. And with then would be typically when you do application, not safety critical one, but the user application, normally you test functional coverage. When you get the functional right, then you stop testing. If you want to do more critical, I think you need to do more, maybe coverage, code coverage, and so forth, so that you can get more, But you definitely will add computational load because you test more. You need to test more. There's no, in this world, there's no free lunch. You want to get this, you want to be rich, but you want to be lazy. Of course, you cannot get. Then you always have to, compromise. You need to more test. Yeah, you need to have some more load. Otherwise, you cannot. So this is what happened. Okay.
Right. And then goes to the next question. Most of the tests are exhaustive search tests. Are there any more optimum testing search, such as dynamic programming or breadth first search?
Yeah, definitely. Yeah, definitely.
Yeah.
You can search. You can do model T-way testing, different techniques, optimize it. They're open problems. You can, if you find a new techniques where you can minimize set of tests, you can. Okay. For the past, I think 10 years, we did so many work on how to get a good set of test cases, and we typically use almost all meta-heuristic that you know of. We have tried. We have used Q-learning. We have used fuzzy. We have used hyper-heuristic to generate set of tests. It's an open problem. You can, because uh, there's a new sort of area called uh, product lines, software product lines. When you have to have software product lines, we have a lot of constraint problem with software product line. This is actually a subset of T-way testing. You can look into software product, and there are a lot of work in software product where you have the parameter can go to thousands, okay, and with value, but with values too, but highly constrained environment, and you can use many techniques, and people use this um, uh, different some constraint solver to solve this problem, and it's actually part of T-way testing. A lot more, the many ways you can do, and there's a lot and open research. I think for the past 10 years, I've published many in good Web of Science, even Q1 journal, doing T-way testing, but doing different techniques, even constrained one, unconstrained one. So yeah, you can use other techniques, dynamic programming or BF search, whatever. Okay.
Okay. So, all right. We go to the next questions. How can we have confidence, or how can we ensure that our testing is proper, is done properly.
Is a difficult. Okay, let me give you this argument. Okay, let's say person A have 10 test cases and a person B having 30 test cases. Okay, which actually is a good one? Another person having 30 test cases and one person have 10 test cases. Can you say that the 30 test cases is better to test the plot than the 10 test cases?
No.
It depends. Okay,
Yeah.
if the 30 test cases is coming from the same partition, let's say the partition between 10 to 100. From 10 to 100, yes, 11, 12, 15, 16, all. You have many test cases, but from the same partition. That even if you have 30 test cases, and his test case is of low quality because he has the same partition. But if somebody has only, let's say, 2 test cases, this invalid partition, valid partition, and in boundary, he has better test cases than the other guy who have 30, but of the same partition. So the number of test cases does not tell you the quality of the test. It does not, because it depends on how you generate the test case. So if you have 30 test cases of the same partition, and the other guy only 3 test cases, but all different partition and at the boundary, the guy with 3 test cases is better.
Yeah.
Although he has only 3 test cases.
Yeah.
So a lot of people thinking in testing that the more I test, the better I am. No, it depends. So you really have to sort of plan your test. You know, what are tests, and have you? If I were you, I would, okay, this kind of problem, I'm going to test with T-way. I'm going to test with different technique. You know, I'm not just going to stick with one and say, okay, because if you say for T-way testing, if there's no fault when T equal to 2, your conclusion is that the application does not have any two-way interaction. That's the only conclusion you can make. You cannot say that the software is actually error-free. You cannot say, because you can never know, but you can know that there's no two-way interaction. So you need to have other test techniques for you to generate the test case for you to do testing. Okay,
right.
So that is the answer.
Okay, and now the question from Wahana: is T-way strategy is applicable for all software or particular software?
Okay, it's like I said. Adakah saya cakap bahasa Malaysia sekejap ya? Adakah kapak itu sesuai untuk semua jenis untuk motong semua jenis barangan? Atau kalau kapak itu X, yes, X, isn't it? Kapak itu tahu tak kapak? Bukan minyak kapak, itu lain.
Bukan.
Kapak itu macam potong tebang pokok itu.
Ya.
Ya, kalau adakah kapak itu sesuai untuk semua memotong semua apa saja barangan? Tidak. Kapak itu hanya untuk pokok atau benda yang keras. Tapi kapak itu tak sesuai untuk memotong kek. Boleh potong kek, tak ada masalah. Tapi adakah sesuatu yang sesuai? So the same question is that adakah T-way ini boleh applicable kepada semua jenis software? So jawapannya kita kena lihat, we have to look into case by case basis whether that is actually suitable. So this is why to be able to do a good tester, you need to have a feeling of the kind of, okay, this kind of application, what kind of test technique, test data generation technique I'm going to use. So I'm not going to, I learn only one, okay, this satu ini, one size fits all. Learn satu, semua boleh pakai. It's not like that. It's not like that. You really have to have knowledge on how to use it. So, okay, any more?
Yeah. Well, there's a repetition question. How do we prioritize test case? I think you have answered that question before.
Okay. There, I actually, to be honest with you, I've skipped many details when I give, because I'm worried of time, because I too many technicals. Then I'm worried that we get stuck into technicalities. So there are, for example, in T-way testing, there's something called constraint, where, for example, some set of test cases are deemed impossible. For example, if you test, for example, a pizza, you have vegetarian, then if you set vegetarian, beef is impossible to be there. You can put constraint inside that. That means in your application, you want to test whether or not the constraint is actually happened that the user is making mistake, where something impossible is also put in the system such that the system will crash. Something cannot happen, but you put in and you can use constraint to do testing also, T-way testing. So it's actually T-way testing is actually one of the tools you can imagine be able to complement other techniques in software testing that you can use T-way testing. It depends on application, but when you have combinatorial problem, when you want to select between different selection of stuff, then combinatorial is good way to do this. But when you have something that is, decision coverage, this kind of thing, combinatorial testing is not quite useful. So you really have to know this kind of problem by experience that you use to be able to use it effectively. Okay.
Right.
So any more?
Right, Professor.
Okay.
I don't think so.
All right.
All right, Professor. As a closing, it would be nice to hear a brief notice from you, please.
Okay. Yes. Concluding remark. You mean?
Yeah.
Okay. Okay. I think I'm very happy. I'm very honored to be able to give my 1 cent worth of knowledge. What I had is actually, if you look at in the sea, there are a lot more knowledge, but what I have is most tiny bit of knowledge that I had. Okay, then being able to share to many of you. I'm very happy to be able to do it. I'm really thankful to Dr. Adi for being so-called very patient with me, because he asked me, can you give me my picture? So I gave him one. And he asked me 3 things, but I gave him one. Okay, this one later. Okay, this one later. So he'd be very patient and then to everybody for listening to this. Thank you so much. I hope that this is not the first time, not the last time we all meet together. Maybe one of you want to come to UMP, maybe to, I don't know, to write paper together or write research paper together, whatever. I'm very glad to I'm actually, I like to do writing, I like to do research. So even though I'm busy with many things, I know, but you can always contact me. You can get my phone number. Even I'm okay with the phone number if you want to ask something. So with that, thank you so much. Thank you.
Okay. Yeah.
Maybe one question, Mr. Reddy, to Prof. Kamal. There is any opportunity to get some scholarship from Prof. Kamal for pursuing maybe master or PhD program?
Okay, there are two things. Okay, UMP we have so-called matching grant.
Yes.
Meaning that you can apply. UMP can give up to 20,000 ringgit.
Okay, nice.
10,000. I think 10,000, 20,000 ringgit. But you can do a matching grant. You give 20,000, UMP gives 20,000, and then we can work together on a project. I also have a grant myself. Okay, so I do a lot of this T-way testing. So if you're interested, you can send something, and we can have a look. I'm expecting one student from Indonesia in January. So my project. So if you I'm looking for someone who's a software engineering background and good programming.
Okay.
With that, then we can. And we publish a lot of because I put very high standard to my students. You want to graduate, you have to get one ISIQ one. So then, if you work with me, then we can get one. It's good for you. We like that. We put this stress to the students so that the student can do it, but they just don't believe in themselves. That's all. When they believe in themselves, they can do it. So that's my last. Okay.
Thank you.
So welcome to, if you want to do a grant together, fine. We can work. We have many matching grants. You can do five. I'm not sure. How much is 10,000 in Indonesia? Is that a big money or is that a
10,000? Yes.
That's the minimum 10,000.
Yeah, 10,000 is big. It's very big. 30 million.
We can go until 40,000. You know, matching 40,000.
Oh, 40,000.
You give 40,000, we give 40,000 back.
Okay, good.
That's matching. Okay.
Yeah, unfortunately, the deadline for the grant is
Now it's open.
last night. So maybe next next year we will try to apply matching grant, because last night I tried to apply the grant, but like so the.
Okay, Dr. Feda is also can get the grant, so you can
exactly.
work with him also.
Yeah.
The only thing is because I'm the one who hold the grant, because it's under my portfolio, so I know the grant better. Okay.
Okay. Thank you.
All right. Thank you so much, everybody. Thank you.
Right.
Okay.
Thank you, Professor Kamal, for sharing knowledge to us. And thank you for all participants for your kind attention. I do apology for any inconvenience you may experience. Goodbye and good luck. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor T.S. Dr. Kamal Zuhairi bin Zamli, for the amazing lecture.
And thank you to Mr. Edi Suharto STMCom for moderating the lecture.
Before we continue, we will have a virtual photo session together.
Okay.
To all guests and participants, we would like to ask you to turn on the camera.
Okay. To all participants, we would like to ask you to kindly turn on the camera for the virtual photo session together. Maybe we will start from the first page. Okay. Okay, some of them are still turning on the camera. Okay, Catherine, are you ready to take the photo? Okay. In the count of three.
1, 2, 3. Say cheese. Okay.
Okay. To the second page. There are some. Okay.
Now for the second page. Okay. There are still lots who
hasn't turned on the camera, yeah, I guess. Okay, it's okay. I think we will count to three for the second page. In the count of three. 1, 2, 3. Smile. Okay. Okay, thank you. The photo session is finished.
Thank you all.
Thank you. Once again, we would like to thank Professor T.S. Dr. Kamal Zuhairi bin Zamli from Universiti Malaysia, Pahang, for the amazing lecture. Hopefully, we can meet again in another visiting professor lecture.
Yeah, thank you.
Now we will have a break for 13 minutes until 4 p.m. To all participants, we will continue this session after the break with a lecture from Dr. Heuristic.
Oke, untuk teman-teman peserta akan ada istirahat untuk selama 13 menit, nanti akan kembali lagi pukul 4 sore. Oke, sekian. We would like to thank once again to Professor T.S. Dr. Kamal for the lecture, and see you guys on 4 p.m.